Okay, so today we are talking about dynamic arenas in C. Now, in the last video, I showed you guys this example of a linked list, and we stored the linked list inside of an arena. And if you remember, an arena is just a buffer with an offset, and we can allocate memory on that buffer just by moving the offset by the number of bytes we need. So, I want you to think about a circumstance where we were allocating lots of nodes, right? So not just 3 nodes like this, we're allocating many nodes. What would end up happening is we will occupy the entire arena and it'll be full. So how can we tackle this problem of having a full arena? Well, one kind of naive way to do it would be, okay, this buffer is full, we can allocate a new buffer, which is much larger, then copy all the contents of this buffer into that new one. And that could work, or that would work, but it's quite expensive computationally because we have to allocate a new buffer. We don't know if it's going to be allocated in place, and then we also have to copy all the data back into that new buffer. So that is a method, but there are 2 other methods I want to show you guys, which I think is much more powerful. Now, the first method is going to be a linked list. So we have this buffer right here, which contains some data in our arena. Now this buffer is full. What we can do is we can allocate a new buffer of the same size. And then we can make our current buffer, which is full, point to the next buffer. So you can think of this as a linked list of buffers or nodes, where each node just contains a large buffer. And then once one of these buffers is full, we just allocate a new node of the same size and just continue allocating from there. So in this example, the first buffer is full, I then allocate a new buffer, the same size, and then I just continue allocating memory on that buffer. So allocate another node, offset's 28, allocate another node, it's 32. And we can just continuously do this for all of the elements you want. And the nice thing is, we can actually construct a lot of these, we can turn into a linked list, we can construct a lot of these buffers and connect them together. Now, one thing that we have to be very careful about here is these nodes will always be the same size. So we have to make sure that the node is not too small, in which case we will end up having to allocate lots and lots of nodes, and that will just be wasting memory. In the same time, not wasting memory, but it'll be quite computationally expensive. If our nodes are too large, then we won't be allocating nodes very frequently, but we might be wasting memory because we have such a large node and we're only occupying a very small amount of it. So this is the linked list strategy. However, there is one final method which I think is the most powerful one. But to understand how it works, we have to take a little bit of a detour and understand something called virtual memory and how memory is actually used at the operating system level. So we have physical memory, right, which is the RAM. So whenever you're building a computer, you're going to put those little RAM sticks next to the CPU. That's what we call physical memory. And the operating system splits this physical memory into pages, and each page is 4 kilobytes, right? Or on most 64-bit systems, it's 4 kilobytes. Now let's assume that I've got a computer with 16 gigabytes of memory, so I've got lots and lots of pages. The OS also has something else called virtual memory, and virtual memory also has pages. However, on modern 64-bit systems, you can have up to 256 terabytes plus of virtual memory. So you're thinking, like, how is that possible? I've got 16 gigabytes of physical memory and 256 terabytes of virtual memory. Well, you have to understand that virtual memory is an abstraction on top of physical memory. Virtual memory is just a range of addresses. And the way it works is that whenever we start a process on the operating system, the OS will just allocate some pages of virtual memory, so just some addresses in virtual memory. And then when we need to actually use the data or write some data into memory, it maps those virtual addresses into physical memory. Now this will look something like I'm going to show here. So I've started a process, let's say it's my program, and I allocated 4 pages. That's going to be 16 kilobytes of virtual memory. Now, from the program's perspective, it's going to be 4 pages which are contiguous, they're right next to each other. However, the OS is free to put these pages wherever it wants in physical memory. So how does it do that? Well, we have a data structure called a page table the OS manages. And what happens is all of these pages in virtual memory are referenced in the page table, and then they are allocated pages in physical memory when we need them. So the OS does not have to store these pages contiguously in physical memory. It can store it however it finds convenient. And this has numerous advantages for the OS. From a security standpoint, this is much safer because if we do not have virtual memory, then the OS will be like, okay, so I've got a free page right here. Or let's say it's got a free page right here. It's going to give us a page here. Then it gives us another page here. But another process is using this page. So whenever we are trying to go through our memory or iterate over our memory, we have to make sure, okay, these 2 pages I can iterate over fine. I can just access these pages. But I can't have to be careful to jump over 4 kilobytes because this page right here might be given to some other process. If I try accessing it, then the program will segfault and won't run. So therefore, the OS just creating the virtual memory abstraction. From the processor's perspective, the memory is contiguous, and the OS is able to map it to physical memory however it likes. It also prevents other issues like memory fragmentation, a lot of other problems, which I won't really get into. But as you can see, it's a very useful abstraction to have. Now, another thing is, whenever let's say I removed a page from virtual memory, that corresponding page, the OS will go to the page table, and then it will remove the corresponding physical page which was allocated. Now, another very useful property of virtual memory is that it's split into 2 parts. The first part of using virtual memory is reserving the pages, and then we have committing the pages. So whenever we reserve virtual memory, we're just telling the OS, okay, this range of virtual address space, these pages, these ones will be used by my process, so just reserve them. Don't let any other process, don't give it to any other process, just let me have them. And what happens there is, I can reserve 2 pages, but I won't have any physical pages mapped to it because I haven't stored any data. When we commit a page, that means we're going to start storing data at those addresses. Then the OS has to go to the page table and then map it to a physical page if it's available. So this is a general idea of how virtual memory works. Now, this reserve and committing process is very powerful because it allows us to do some interesting things with our arena. So if I bring back the arena example we had before and have an empty arena, what I can do is I can reserve a lot of virtual memory. So I can do like 10 gigabytes of virtual address space. I can just reserve all those pages. But it does not matter because I won't be using 10 gigabytes of physical memory. I just reserved those pages in reserve those virtual addresses. So what I can do then is, let's say this arena is split into 4 pages, as we've shown here. Of course it's not, it's 10 gigabytes of many more pages, but as an example. So then I allocate a node. What's going to happen is, my offset pointer is currently 0. It's moving 4 bytes, I'm going to move forward. Then allocate a node there. When I allocated a node on this page, then I basically told the OS, I'm storing data here, commit this page. Then the OS went to the page table, and then it mapped the virtual page into a physical memory location, or a page in physical memory. So if I allocate another node right here, as you can see, so far I've only used 1 page. These other 3 pages are still just reserved. I haven't committed any memory there. So let's just say I allocate some more nodes, and then I end up using now 2 pages. So now I might have reserved 4 pages, but I've only used 2 pages. And that's the important thing to notice. The virtual memory here, these pages right here, they're reserved, but they're not committed. So they're not actually being mapped to any physical memory. It's only when I start storing data in them, I ask the OS to commit that page. It will then create an entry to the page table. Then it will map it to a physical page. So I'm going to show you guys an example of how we can do this. I won't write down an example of the linked list method I showed you guys before because I think that's pretty self-explanatory. It should be too hard to implement. But this technique is a lot more hands-on because it requires some OS-specific functions. Okay, so here I've got the code from the last tutorial where we made a basic arena. Now I'm going to extend this so that we can reserve a lot of virtual memory, a lot of virtual pages, and then we can commit those pages when we need them. So the first thing I need to do is find out, okay, how large is the page size on my operating system? On most 64-bit systems, it's going to be 4 kilobytes, right? but I want to be sure how large they are. So the operating system gives us some of these functions. On Windows, we've got the get system info function, and this will just tell us, it will take in a system info struct, and then it will fill out the struct with some info that we need. One of the members right here is DW page size. This tells us the size of each page in bytes. So what I'm going to do now is just in the arena init function, I'm going to create a system info struct. So I say system info, and then I'll use get system info, and I'll pass in a reference to this. Okay, so we need to import windows.h for this to work, and yeah, okay, so that works. Now if I open up the debugger here, I'm using Visual Studio, we should be able to see that if I break out this line, it looks like address sanitizer is crashing, so I need to fix that. So this sometimes happens whenever using address sanitizer on Windows. It sometimes crashes when something goes wrong in the debugger. So if I open up Visual Studio again, and then I try, there we go. So if I type in system info right here, you can see the structs being filled out with some values. And right here we got DW page size, so that's 4096, so 4 kilobytes as we expected. So I can just use that right here. I can store that in a variable. So I'll say I'll have 2 more variables here, say unit64t, which will be page size, and then I'll have another variable called number of pages allocated. So this is how many pages the arena is currently using, right? So I'm going to do here, I'm going to fill out page size is equal to system info dot dw page size, and then the number of pages allocated will just be set to 0 by default, because we haven't actually committed any physical memory just yet. When we start storing data into the arena, then we'll start allocating pages as necessary, or the committing pages. So the next thing we have to do is modify the arena alloc function. So right here, what we need to do is we need to check, okay, do you have to allocate a page here or not? If we do have to allocate a page, then we will commit the page, otherwise we will not. Actually, I forgot something. Before we do that, we need to first remove this malloc pool right here. So malloc will reserve and commit the memory. Well, theoretically, what it usually does is that it's not guaranteed to give us all the pages until we start using it, but what I want to do here is replace this with something called virtual alloc. So with virtual alloc, this gives us a lot more fine-grained control over, are we reserving pages, are we committing pages, so what are we doing? So if I go back to documentation right here, we have the virtual alloc function, so we can reserve, commit, change the state of pages, virtual address space, and we can also commit them. So what it will take is an address. I'll set this to 0 by default. So if I do 0, then the OS decides where it's going to store the where it's going to start storing the allocation. DW size is going to be the amount of memory that we want to allocate, or how much virtual memory we want to reserve. Then FT allocation type is going to be mem reserve, mem commit. We're going to first reserve the virtual address space, and then as we need to commit pages, we use mem commit to do that. Then we have one last parameter right here called FL protect. I'm going to set that to be page read write. This should work fine. So the equivalent of this function on Linux is mmap, but I won't go into that because I'm using Windows, but you can read the documentation here. It's a lot more, it's very similar. So I'm just going to quickly copy this, then we can start writing the code for that. So I'll say, I think I copied the wrong function as virtual free. So then right here, I'll paste this in. And I'll fill them out. So 0 for the address. Size will be buffer size. And then the allocation type will be mem reserve. And then FL protect will be page read write. Okay. And then we'll just say buffer is equal to that. So now that we've reserved all this virtual address space, in the arena unlock function, we can go ahead and check, okay, do we need to allocate a page for this? We need to commit a page or maybe several pages for this allocation, depending upon how large it is. Well, then we can do some checks right here. So the first thing I want to do is find out, okay, how many pages will this allocation take? So what we can do here is I'll say something like divisor is equal to the arena's current offset plus the padding plus the allocation size. And then I'll divide this by the arena's page size. Right. So what am I doing here? I did too many parentheses. So divisor will basically tell us how many pages this allocation will take. So let's say I'm allocating 5 kilobytes, right? The whole allocation with, you know, the actual allocation size and the padding together is equal to 5 kilobytes. And I've currently got 0 pages allocated. What I'll have to do is actually allocate 2 pages, because this one page is 4 kilobytes, so that's 1 page gone for the first one, and then 1 kilobyte later we have to allocate a whole new page for that, so that will be another page. So I have to allocate 2 pages for that. And then I'll also add 1 right here, because sometimes let's say this divisors, let's say our current allocation, or rather the amount of pages we allocated is 3, and then divisor is something like 5.23. What I'm going to do, actually before I do that, I'll quickly just write down some code to show you guys how this works. So I'll say here, if divisor is greater than arena's current number of pages allocated, then we will find out how many pages we need to allocate. So say num of new pages to allocate is equal to uint64t of divisor minus arena's number of pages allocated. Right. So what am I doing here? Divisor is currently a double, so let's just say I've allocated 3 pages and this allocation requires 5.34, for example. What this calculation does right here is it finds out how many new pages you have to allocate. So you might be thinking, okay, that's 5.34 minus 3, that's equal to 2.32, right? What I'm doing here is I'm actually casting it to an integer. So we're going to have to add in a 1 right here. Right, I have to add in a 1 because I have to, in the case that there's a decimal right here, I have to consider that case. So I'm just going to add in an extra page just to be sure. So then what we can use is virtual alloc again. But this time we're going to give a pointer. I'll say uint8 pointer. So it's going to be 1 byte at a time. It's going to move. So I'll say buffer plus arena current offset. So this is, we haven't actually changed this is the original offset before with the allocation. We actually update the current offset right here. So this is before then. So this is going to be the current address we are at. So this should be inside of a page. What we're going to do is we're going to allocate the number of new pages you have to allocate times by the page size, right? So this is going to tell us how much memory in bytes you have to allocate. And then we also just do here mem commit, and then I'll say page read write. And then if I try to compile this, it does compile. So the last thing we have to do is fix up arena delete. So arena delete currently uses free, but we can't use free anymore because we are using virtual alloc, so the Windows functions for allocating memory. So to do that, we can use a method right here called virtual free. This just takes in the address, which we're going to be the buffer obviously, and then we're going to tell it the size of the region of memory to be freed. That's going to be the current offset of the arena. And then we're going to just tell it the type. So you have mem decommit and mem release. Mem decommit just decommits the pages which that memory occupies. Mem release just decommits those pages, also frees up the virtual address space. So in the next video, right now we're going to use mem release, but in the next video I'll be talking about sub lifetimes with arenas. Then we can use mem decommit. And what that allows us to do is basically pop off pages of the arena when we don't need them. So when let's say we use 10 pages, and then we should like free off some memory in the arena, then we only have to allocate we have to decommit 3 pages, but we can still keep that virtual memory reserved for future use. So what I'm going to do here is in free, I'll replace this with virtual free, and then I'll say submit arena's buffer, then arena's current offset, and then mem release. If I compile this and I run it, okay, it still does work. So what I should be able to do now is allocate a humongous, actually to make this work I have to use gigabytes. Let's allocate 10 gigabytes. I'll create a macro for that. So I can say something like int array is equal to arena alloc arena, let's say 1000 size of int, then I'll say line of int, and this still works, right? We're able to allocate the arena. So I said let's make int array at let's say 599 is equal to 600. If I try printing that out, that should work because I've preserved a lot of virtual memory, but it starts committing the pages when we actually start storing data in the arena. So I hope you guys found this video useful. In the next video, I'll talk about sub lifetimes and Scratch arenas, which you will find very useful to see how you can really use arenas in a proper project, because there are some issues with arenas so far. And I hope you guys enjoyed it. I also made a video a couple of weeks ago about hash tables in C. If you enjoyed this video, you probably enjoyed that one as well. And I'll see you guys later. Bye.